All right, let's go ahead and get started. Would you mind closing the door? Yeah. Okay. Today's lecture is going to blow your freaking minds. So I'm very excited about today's lecture and next Tuesday's lectures because they're really, I think, the most exciting lectures in this course. I'm very, very excited. But before blowing your minds with the amazingness of today's lecture, what I would like to do is just start by reminding you of where we ended up last time. So last time I introduced a new formulation of the laws of mechanics. So I introduced the Hamiltonian method for formulating the equations of motion of a mechanical system. And the basic idea was the following. So if you have a mechanical system with n degrees of freedom, qi, and Lagrangian, which depends on qi dot, and time, then the one way of computing the equations of motion of the system is to simply write down the Euler-Lagrange equations that arise by minimizing the action with respect to variations in Q. But another way of writing out the solutions to the equations of motion is you first define the momentum pi, which is conjugate to the dynamical variable Q, by differentiating the Lagrangian with respect to Q dot. We define the Hamiltonian, which is the sum over I, pi qi dot, minus the Lagrangian. And then we proceed to write that as a function of the p's and q's. So we solve equation 1 to write the qi dots in terms of qi and pi, and then use that to write the Hamiltonian as a function of the p's and q's. And finally, the equations of motion are Hamilton's equations, which are a set of 2n first-order differential equations, which say that qi dot is dh by dpi, and pi dot is minus dh by dqi. And we think of the pi's and qi's as making up some 2n dimensional space called phase space. So each point in phase space specifies a position and a conjugate momentum, and that uniquely specifies the state of the system. And the evolution of the system is a flow on phase space which is generated by this set of first-order differential equations I wrote above, which are Hamilton's equations. And if we wish to think intuitively about Hamilton's equations, we first imagine the Hamiltonian as a function of points on phase space. We compute the gradient of that function. And this flow equation says that the time derivative of Q and P points in the direction of the vector perpendicular to the gradient of a Hamiltonian. So that gives us a very nice geometric way of thinking about the Hamiltonian evolution of a dynamical system. And the advantage is that time evolution is now given by some first-order differential equation. And as you all know, first-order differential equations are much simpler than second-order differential equations. And that's one of the real advantages of this method. So are there any questions on this before I continue? And last class we went through several examples of working out this procedure for a couple of simple mechanical systems. Now, the real advantage of the Hamiltonian framework is that it treats the momenta and positions on equal footing. So the momenta pi and dynamical variables qi are treated on equal footing. And that is quite different from the situation in the Lagrangian formulation. So in the Lagrangian formulation, the equations of motion are found by varying the action with respect to q, but the p's play no role in that formulation of the equations of motion. They're simply quantities that one can construct, which may or may not happen to be conserved depending on the detailed form of the Lagrangian. So, in fact, it turns out that because the Hamiltonian formulation treats positions and momenta on equal footing, one can also understand the equations of motion as coming from varying a path on phase space, not just a path on configuration space. So let's try and understand how that works. So let's recall Hamilton's principle. Everything's named after Hamilton today. So Hamilton's principle, or the principle of least action, says that if you start out in the Lagrangian formulation with an action which is given by the integral of a Lagrangian, so you construct an action which is the t integral of the Lagrangian, and this action is extremized on a solution of the equations of motion. If you work out the variation of the action with respect to q and you set it equal to 0, that gives you the equations of motion of the system. And so this was a statement that every mechanical system satisfies a minimization problem, where what you are minimizing is an action regarded as a path through configuration space. So here, the action is regarded as a functional of paths through configuration space. Now, it turns out that the exact same thing is true if one also regards the action as a functional of paths through phase space. So, in the Hamiltonian setup, we may regard the action as a functional not just of the position of the system as a function of time, but also the momenta as a function of time. And how is that action defined? Well, the action is the integral of the Lagrangian. The Lagrangian is h minus p q dot. So that means that, the Hamiltonian was p q dot minus L. So the Lagrangian is the sum over I, pi qi dot minus the Hamiltonian, regarded as a function of pi and qi. So if you have a system with dynamical variables q and conjugate momenta p, then you can write down the following action, which is a functional both of q and p, and is given by this formula, the sum over I p q dot minus h. And so instead of the previous formulation of Hamilton's, the Hamiltonian principle, here this is a functional of qi of t as well as pi of t. So whereas previously we imagined an arbitrary configuration qi of t, an arbitrary path of the system through configuration space qi of t, here we're imagining that we have some phase space, q and p, and if we want to understand how the system evolves from one state to another state, you could write down an arbitrary path through phase space that connects those 2 points, and consider the action as a functional of that path. And the important point is that whereas in the Lagrangian point of view, P is constructed out of Q. So P and Q are not regarded as independent variables. In the Hamiltonian approach, you regard P and Q as independent variables, so we can imagine varying P and Q separately. So, just to remind you, the way that one minimizes an action functional is you vary the functions on which the action depends, in this case P and Q, and you look at the term which is linear in the variation of P and Q, and you set that equal to 0. So, yes? Okay. So this was the action, and we imagine taking P to delta P plus delta P, and Q to Q plus delta Q, where Q and P are functions of time, and likewise delta P and delta Q are functions of time. So any question on this setup? And we would like to now ask how the action changes as we vary P and Q. And we will look at the variation which is linear in delta P and delta Q, and set that equal to 0. So everyone remembers this from our study of the action principle? Good. So what's the variation of the action? Well, we just look at this formula up here for the action, and we regard it as a functional of P and Q as separate variables. So P and Q are not related in any way. Well, that's the integral dt of a sum of a variety of terms. So there's a term which comes from varying P, plus a term which comes from varying Q. Here, let me try and get this a little higher. So Pi delta Qi dot. Plus a variety of terms which come from varying the P and Q on which the Hamiltonian depends. So those we can compute using Taylor's theorem. We just compute the Taylor expansion of H to linear order in delta P and delta Q. And so varying P, we have dH by dP times delta P, and dH by dQ times delta Q. That's just, well, I guess that's just the chain rule for writing out the derivative of H as we vary P. Or you could think of it as the Taylor expansion of H to first order around P in the perturbation delta P. Okay. So we can now play the usual game and write this as a term which is linear in the perturbation in delta P and delta Q. So we have an integral dt of the sum of two terms. So let's first look at the term which is proportional to the variation of P. So that will be Qi dot minus dH by dP times delta P, summed over I. Now what about the term which is linear in delta Q? So recall that in the derivation of the equations of motion in the Lagrangian formulation, we had to integrate by parts to write a delta q dot term in terms of something times delta q. So I'll use the fact that the integral dt of pi delta q dot I is, upon integration by parts, minus the integral of pi dot delta q plus a boundary term, which is just computed by the fundamental theorem of calculus, which is pi delta qi. And if we're integrating from t1 to t2, it's just this boundary term evaluated at t2 minus that evaluated at t1. So just writing that up here, we also have a term proportional to delta q, which is minus pi dot minus dh by dqi times delta qi. And then we have plus a boundary term. But if we take our variation such that the variation of delta q vanishes at the boundary, just as we did in the derivation of the action principle in the Lagrangian formulation. Remember, we only varied over all configurations with fixed endpoints. So we imagine fixing q at the endpoints here, but varying only over delta q that have the same endpoints. So delta q will vanish at the endpoints. That means that this term will vanish. And so we see that the variation of the action then is the sum of two terms. We have one term proportional to delta p and another term proportional to delta q. And so in order to minimize the action as a functional of p and q, we need to set the coefficients of delta p and delta q to be 0. So this is minimized only if the coefficients of delta p and delta q equals 0. And the coefficient of delta p being set equal to 0 says qi dot is equal to dh by dp. And setting to 0 the coefficient of delta q, we see that pi dot is equal to minus dh by dq. And those are the equations of motion in Hamiltonian form. So these are Hamilton's equations. So the Hamiltonian principle is actually much more powerful than I led you to believe at the beginning of the semester. Not only can I vary over all paths through configuration space, I could also vary over all paths through phase space, where the position and the momenta are varied separately. Now, this is a little counterintuitive in the following sense. If you imagine, say, a particle moving through space, then you could set x of t to describe some curve through configuration space. And you would think that if I specify x of t, then I also specify the momentum, because the momentum is just the mass times the velocity, so mx dot. So it would seem counterintuitive that one can vary the position and the momentum separately. But it turns out that mechanics, the form of mechanics, the Hamilton's principle, can be formulated even allowing the momentum and the position to vary separately. So even if the momentum is not equal to x dot, the fact that the momentum is equal to x dot is a consequence of Hamilton's formalism. It's one of the equations that you can derive by minimizing the action. It's not something you need to put in by hand. And so this, I think, fact that the Hamiltonian principle treats momenta and positions on equal footing really lies at the heart of many of the things that we are going to be discussing for the rest of the day and for next class. And this observation that the least action principle can also be understood in the Hamiltonian framework is merely the first such observation that we will make. So are there any questions on this derivation before I continue? Yes. Take any function which is not x dot. So for example, so let's consider a free particle. So in the Lagrangian setup, we consider x as a function of t, and we let p be defined to be the mass times x dot. And we treat the momentum as something which is not an independent variable, but which is a dependent variable. It depends on x of t. But it turns out that we can treat the mass and the momentum completely independently. So we can imagine x of t being the position of the particle, and p of t being some arbitrary function, which is the momentum of the particle, which are not related by the formula p equals mx dot. So instead, the formula p equals mx dot is one of the equations of motion of the system. So if the Hamiltonian is, say, 1/2 m 1/2 p squared over m, then the Hamiltonian equations say that q dot is dh by dp, which is 1 over 2m p. Sorry, I guess I should call that x dot rather than q dot. And the other equation says that p dot is equal to 0. No 2, sorry. Thank you. Yeah. So you can see that the statement that p is m times x dot is not an input. It's an output. It's one of Hamilton's equations. So in a sense, the statement that momentum is mass times velocity is an output. It's one of the equations of motion. It's one of Hamilton's equations, which is derived by minimizing the action. So rather than an input, it's more a matter of point of view than anything else. But as we will see, a formalism where momentum and position are treated on equal footing is extremely useful. So yes, there was another question. Okay. Is that, hopefully that makes it a little more clear. Yeah. Okay. Good. Any other questions?
Well, just to also compare from this one, you said that this is an output, the equation equals mx dot, but here we know also how the kinetic energy relates, how we can replace the velocity with the t.
Yes.
So it's still an output.
Well, it's really a question of your point of view. I mean, if you did not know Newtonian mechanics, where momentum is mass times velocity, then you would see this would be an output of our formalism. It's an output in the sense that it is a consequence of the statement that we minimize the action as a function of x and p. That's the sense in which it's an output. Any other questions? Yes.
Sorry, so Newtonian mechanics saying F equals mx, that only goes when t equals m times x dot.
Well, absolutely. There's certainly plenty of cases. There's certainly plenty of situations where the momentum is not just something times x dot. We've already encountered many of them in this class. Last lecture, for example, we did a particle on a parabolic wire where the momentum was 1 plus x squared times x dot, something like, or x dot over 1 plus x squared, I forget. And so in that case, it's still the case that p dot is dh by dq, but it's not the case that x dot was just equal to something times p dot. X dot was dh by dp, which is, in that case was not just p dot, but rather some function of x times p dot. Some function of x times p. Yeah. So this is a lesson that I really think it is important to internalize, which is that the momentum conjugate to a variable is not just the time derivative of that variable. It's something more complicated. A very simple example is a free particle moving in 2 dimensions in polar coordinates. In that case, the momentum conjugate to phi is not phi dot, it's phi dot times r squared over r squared. R squared is another coordinate of the system. I mean, it's another dynamical variable. So that's probably the most basic example. So even for a free particle, if you write it in polar coordinates, the momentum conjugate to phi, which is the angular momentum, is phi dot over r squared. So it depends on the dynamical variables, in this case r. Any other questions? Okay. So I've gone on and on last class and today about how useful Hamiltonian mechanics is, and how it really gives you a formalism for mechanics which is very familiar to the formulations of quantum mechanics that you have seen. And I would now like to tell you exactly what I was talking about. And so I would like to continue our study of phase space and the Hamiltonian formalism by introducing a notion of what's called a Poisson bracket. And so this gives us a formalism of classical mechanics which you will find very familiar because it resembles quantum mechanics. Now, of course, that statement is very non-historical. The correct statement is that quantum mechanics resembles the Hamiltonian formulation of mechanics. But unfortunately, that's not how these subjects are structured in your mind. So let's begin by thinking about phase space. So phase space is the set of all q's and p's. And in the Hamiltonian formalism, you're never supposed to think about q dot. You're only supposed to think about the momentum p. So let's consider 2 functions which depend on the state of the system. And so there are 2 functions that depend on where you're sitting in phase space. So let's call one of them f. So that's a function of the qi's and the pi's. And let's call the other one g, which is a function of the qi's and pi's. For example, f could be equal to q1, or p2, or q1 p2 minus q2 p1, or something like that. And let's define the following. So define the Poisson bracket of f with g to be the following. It's the sum over I of the derivative of f with respect to qi times the derivative of g with respect to pi minus the derivative of f with respect to pi times the derivative of g with respect to qi. So f is a function of q and p, so we could write down the partial derivatives df by dq, df by dp. Likewise for g. And here I am just forming a particular combination of those derivatives and calling it the Poisson bracket. And I denote it by these curly braces. So what properties does this Poisson bracket have? Well, the first property that they have, which is probably clear to you, even from this definition, is that the Poisson bracket of f with g is equal to minus the Poisson bracket of g with f. Why? Let's stare at the definition of the Poisson bracket. And if you switch f and g, you have dg by dq times df by dp minus the same thing with q and p reversed. And because of that minus sign, that's equal to minus the Poisson bracket of f with g. So this is the statement that the Poisson bracket is antisymmetric. Okay, well that's good. So now let's imagine that we have a function f which is a sum of two other functions. Say it's a constant alpha times f plus beta times g, and we take the Poisson bracket with a third function h. Well, so here alpha and beta are constants, and f, g, and h are functions on phase space. Functions of the p's and q's. Well, all we do is we take the derivative of alpha f plus beta g, and that's equal to alpha times the derivative of f plus beta times the derivative of g. So that means that this is equal to alpha times the Poisson bracket of f with h plus beta times the Poisson bracket of g with h. So that is the statement that the Poisson bracket is linear. The Poisson bracket of f plus g with h is the Poisson bracket of f with h plus the Poisson bracket of g with h. And likewise, the Poisson bracket of 2f with h is 2 times the Poisson bracket of f with h. Okay. So that's what happens if you add two functions together and take their Poisson bracket with something. What happens if you multiply two functions together and take their Poisson bracket with something? Well, the product of f and g bracketed with h, how do we compute that? Well, the derivative of f times g is the derivative of f times g plus the derivative of f times the derivative of g. And so that is that's just, I guess, the product rule. And so that tells us that this is f times the Poisson bracket of g with h plus the Poisson bracket of f with h times g. And this is known as the Leibniz rule. And there is a, is that clear to everyone? Okay. Yes? Is there a reason why you put a g after the brackets? If you, okay, the reason is for, it's for dramatic reasons rather than for other reasons. I put it there to exercise your imaginations. And if your imaginations are not sufficiently exercised, I will exercise them more in a minute. Finally, there's a third identity, a fourth identity, so what happens if you take the Poisson bracket of f with the Poisson bracket of g and h? Well, it turns out that if you add the Poisson bracket of g with the Poisson bracket of h and f to that, and also the Poisson bracket of h with the Poisson bracket of f and g, then that sum of those three different terms will vanish. And this is not obvious from what I have written, but I encourage you in the privacy of your own homes to try and prove this. It's a straightforward exercise. You work out a bunch of second derivatives, you add them all together, and everything cancels. And this is known as the Jacobi identity. So, what does this mean? This means that if you have two functions of q and p, you can form the Poisson bracket of those two functions, which is another function of q and p. And this Poisson bracket is antisymmetric in the entries. It is linear. It obeys a Leibniz rule as well as a Jacobi identity. And these identities are all obeyed by the commutator of two matrices. So if you thought of F and G as matrices, and you wrote down their commutator, Fg minus Gf, it would obey all of those four properties. Now, in quantum mechanics, a function of position and momenta is not just a function, it's an operator. And so when you multiply these operators together, you have to use their commutators. And in fact, as you learned in your quantum mechanics classes, these operators are either thought of as finite n by n matrices or infinite dimensional matrices, depending on what system you're discussing. And that fact really stems from the fact that in classical mechanics, you can multiply two functions together using what is known as a Poisson bracket, which has all of the same properties as the commutator of matrices, or the commutator of operators. So the fact that operators don't commute in quantum mechanics is really a descendant of the fact that that functions on phase space don't commute in classical mechanics. Now, you can always multiply two functions of phase space together, and that'll commute. You know, f times g is equal to g times f. But the point is that in classical mechanics, there's another way of multiplying two functions of phase space together, which is known as the Poisson bracket. And this way of multiplying two functions of phase space together does not commute. And so it has all of the properties that the commutator of matrices has. Are there any questions on that? Okay, so let me work out some examples. So let's remember the definition. So the Poisson bracket of two functions is the sum over I df by dqi dg by dpi minus the same thing with p and q reversed. So df by dpi times dg by dqi. So what are some functions of q and p that we could write down? Well, let's take f just to be one of the q's, say qi, q1, q2, something like that. And let's take g also to be one of the q's. Well, if f and g are both just functions of q, then the Poisson bracket vanishes. Because we have, in both of those terms, a derivative with respect to p, which vanishes. So the Poisson bracket of qi with respect to qj is equal to 0. Okay, what happens if f and g are both one of the momenta, pi and pj? Well, again, we have a derivative of f with respect to q and a derivative of g with respect to q that appear in both of those terms. So that will likewise vanish. What if you take the Poisson bracket of qi of a q with a p? Well, let's first consider the case where I is not equal to j. So in that case, we're taking, for example, the Poisson bracket of q1 with p2. Well, in the first term, we'll have df by dq1, which will not vanish. But that'll be multiplied by a dg by dp1, which does vanish. And likewise, in the second term, well, that will automatically vanish, because f is independent of p. So if I is not equal to j, this vanishes. What if I is equal to j? So let's say we're computing the Poisson bracket of q1 with p1. Then that first term just gives you df by dq1, which is 1, times dp by dq1, which is 1, and that second term is 0. So this is equal to 0 if I is not equal to j, and 1 if I is equal to j. sorry. So it's 1 if I is equal to j, and 0 if I is not equal to j. Now, hopefully, this looks a little familiar to you. So in quantum mechanics, you have what are known as the fundamental commutation relations, or the Dirac commutation relations, which say that the commutator of x and p is equal to IH bar. And we're getting exactly the same here, except without a factor of IH bar. So these are known as the fundamental Poisson brackets. So all of that business in quantum mechanics with being confused by the fact that x and p did not commute was not because you didn't understand quantum mechanics, although you didn't. It was because you didn't understand classical mechanics. And now you do. What's that?
It was on a problem set.
Did I?
No.
Quantum? Okay, fine. Well, you have seen it before. They stole my thunder. Okay. Are there any questions on this? Okay. So let's why are these Poisson brackets useful? So let's imagine we have some function f that depends on the q's, the p's, as well possibly having some explicit dependence on time. So f could be q, it could be a q, it could be a p, it could be some complicated function of q's and p's. We would like to understand how this function changes in time. So we would like to understand the total time derivative of f with respect to t. Well, that's easy enough to compute. We just use the chain rule. So there are 3 terms that one needs to consider. So there's the first term, which comes from the dependence of f on q, which itself depends on time. So that's df by dqi times qi dot. And the second term, which comes from the dependence of f on pi, which is df by dpi times pi dot. And then we also need to add a term which is the partial derivative of f with respect to t, which arises if f has some explicit time dependence. Okay. Now, what are q dot and p dot? Well, in the Hamiltonian framework, those are determined by Hamilton's equations. So we have df by dqi times dh by dpi, which was the first of Hamilton's equations. And the second of Hamilton's equations says that pi dot is equal to minus dh by dqi. So the terms in the total time derivative, which arose from the implicit dependence of f on q and p, which are themselves functions of time, takes the form of df by dq times dh by dp minus df by dp times dh by dq. Now, hopefully your memories are not so short that you do not recognize that particular combination of derivatives. That is the Poisson bracket of f with h plus the partial derivative. So the total time derivative of f with t is the commutator of f with the Hamiltonian, plus a contribution if there's explicit time dependence. So to determine how a function evolves in time, we just need to compute the commutator, or the Poisson bracket, with the Hamiltonian. And hopefully you have seen this identical equation in your quantum mechanics class. You have seen this in your quantum mechanics class? Yes. Do you remember it from your quantum mechanics class? Okay, good. Even better. So in your quantum mechanics class, you might have seen this phrased either in an operator language, in the Heisenberg representation, or you might have seen it phrased in terms of expectation values. But the basic idea is that the time derivative of some operator is given by the commutator of that operator with the Hamiltonian. And the point is that that is actually true in classical mechanics as well, provided one uses the correct notion of commutator, which is involving the Poisson bracket. So this is a very nice formula which tells us how any function of P and Q evolves just by knowing the Hamiltonian. And this can sometimes be very useful. So, for example, let's say you have some very complicated dynamical system. And but you don't really care about how all of the various individual degrees of freedom behave, but you only care about how one particular function of those degrees of freedom behaves in time. Then, so like let's say you have a very complicated molecule, for example, made up of 100 different atoms, but you're only interested, for example, in how the center of mass of the molecule behaves. So then you can compute so rather than writing out all 100 different equations of motion and trying to simplify them, you could just compute this commutator to understand how the system evolves in time. And I used the example of the center of mass motion of a molecule not lightly, because that's in fact a very important example. So in particular, if we can find some function I that depends on P and Q, such that the Poisson bracket of I with H is equal to 0, then the time derivative of I will be equal to 0. So that means that I is a constant. So a constant of motion is a function of P and Q which commutes with the Hamiltonian. So, in your quantum mechanics class, you surely talked about conserved angular momentum, conserved momentum, and so forth. And indeed, you were just finding operators which commuted with the Hamiltonian. And in the Hamiltonian framework, the way that you construct conserved quantities is very simple. You just find a function of P and Q which commutes with the Hamiltonian. So, for example, let's suppose that H is independent of Q. Well, that means that H is a function only of P. Well, that means that the commutator, or the Poisson bracket of P with H, will be equal to 0. Because the Poisson bracket of P with P vanishes. And so, in fact, you can show using linearity and the Leibniz rule that the Poisson bracket of P with any function of P vanishes. And so that means that because the Poisson bracket of P with H vanishes, P is a constant of motion. So that is Noether's theorem in the Hamiltonian framework. So this is Noether's theorem. Noether's theorem in the Hamiltonian framework says that a conserved quantity is a quantity which commutes with the Hamiltonian. And indeed, we will see, perhaps this class or next class, that there is an intimate relationship between conserved quantities and symmetries in the Hamiltonian framework as well as in the Lagrangian framework. In a sense, it's a much deeper connection in the Hamiltonian framework. Are there any questions before I continue? No questions? Okay. So let me now take this one step further. So let's suppose that I and J are constants of motion, so that both I and J commute with the Hamiltonian. Then let's compute the commutator, or rather the Poisson bracket, of the Poisson bracket of I and J with the Hamiltonian. Well, let's use the Jacobi identity. So the Jacobi identity says this will be the sum of two terms, one of which is the commutator of J with the commutator of H with I, but the commutator of H with I is 0, so that's 0. The other term is the commutator of I with the commutator of H and J, which is also 0 for the same reason. So that means that the Poisson bracket of I and J with H will vanish. So that means that the Poisson bracket of I and J is also a constant of motion. If you have two constants of motion, you can construct their Poisson bracket to form a third constant of motion. The Poisson bracket of two constants of motion is a constant of motion. So, in particular, if I were to use a mathematical language to describe this statement, I would say that you could think of a vector space made up of the constants of motion. Because if I is a constant of motion and J is a constant of motion, any linear combination of I and J is a constant of motion. So I have a vector space of constants of motion. And for any two elements of this vector space, I could compute their Poisson bracket, and I would get another constant of motion. So that means that the set of constants of motion is a vector space which comes along with a commutator, or with a Poisson bracket. You take the Poisson bracket of any two elements of this vector space, you get another element of the vector space. And in fact, in mathematics, there's a name for a vector space that comes equipped with a way of multiplying two elements together to get another element of the vector space, such that this method of multiplication is antisymmetric, linear, and obeys a Jacobi identity. That is known as an algebra. So in the mathematical language, this means that the conserved quantities form what is known as an algebra. Now, this is not a class on mathematics, so I'm certainly not going to lecture in great detail about what an algebra means and what the consequences of having an algebra of symmetries are. But the short version of this is that anytime you have two symmetries, you can always take their Poisson bracket to find a third symmetry. And that one can proceed in this way. If you start with two constants of motion, you can often proceed in this way to construct more and more constants of motion out of these original constants of motion. And indeed, in your quantum mechanics class, for example, you encountered a case of an algebra, which was the rotation algebra, the SU2 algebra, the SO3 algebra. And we see here that the constants of motion, which are the components of the angular momentum vector in that case, form an algebra. And that's precisely the SU2 algebra that you studied in your quantum mechanics class. There was a question?
Yeah. Would we use two constants of motion to construct this algebra? Is it really useful? Comparing it to two vectors giving a third that's dependent on the first two.
Yeah, I mean, sometimes it's useful, sometimes it's not. For example, many cases it's not useful because the commutator vanishes. For example, if you have a free particle which is moving in 3 dimensions, which is not under the influence of any external forces, then the linear momentum in the x1, x2, or x3 direction will be constants, but their commutators vanish with one another. So that's not a terribly useful thing to consider. What's more useful is to consider the case where the commutators don't vanish. So for example, if you take a particle moving in a central force potential, which depends only on the distance to the origin, then the angular momentum r cross p is conserved. And so, for example, I could write this out explicitly. So L1 is equal to R2 P3 minus R3 P2. L2 is equal to P3 R1 minus P1 R3. And L3 is equal to, oh, I'm sorry, I got my R's and P's mixed up there. R3 P1 minus R1 P3. And L3 is equal to R1 P2 minus R2 P1. And you can compute the Poisson brackets. And you'll see they obey. The Poisson bracket of Li with Lj is equal to the sum over k, epsilon ij k Lk. Where epsilon ij k is the epsilon symbol, or the Levi-Civita symbol, which is equal to 1 or minus 1 if ij and k is an even or an odd permutation of 1, 2, and 3, and 0 otherwise. So, for example, the Poisson bracket of L1 with L2 is equal to L3. So I think I assigned this as a problem on the problem set, so I'm not going to work it out for you. I think I assigned this as a problem next week. Do you want to work it out? No, I think I assigned it as a problem. Should we work it out? Yeah. You want to work it out? Okay. All right, let's work this out. So this is the Poisson bracket of R2 P3 minus R3 P2 with R3 P1 minus R1 P3. And the rules for computing these Poisson brackets are exactly the same as the rules for computing commutators of matrices. You can use the Leibniz rule, you can use the linearity, you could use the Jacobi identity. We won't need to in this case. And so this proceeds exactly as if you're computing the commutator of matrices. And you just remember that the Poisson bracket of R2 with P2 is equal to 1. The Poisson bracket of R3 with P3 is equal to 1, and so forth. So let's look at that first term. So we have an R2 P3, and that needs to be we need to compute the Poisson bracket of R2 and P3 with R3 and P1 and R1 and P3. Now the Poisson bracket of R2 times P3 with R1 times P3 vanishes. Because the only thing that doesn't vanish is the Poisson bracket of R3 with P3. And so in the first term, the only non-vanishing thing is R2 P3 with R3 P1. And in the second term, likewise, the only thing that's non-vanishing is the Poisson bracket of R3 P2 with R1 P3. I'm sorry, there's a plus sign there, yes. Okay, so what's that first term? Well, that's just R2 P1 times the commutator of P3 with R3, which is minus 1. So that's minus R2 P1 plus the commutator of R3 P2 with R1 P3, which is P2 R1. And that is equal to minus L3. Oh, no, sorry, that's equal to L3. R1 P2 minus R2 P1. So the Poisson bracket of L1 and L2 is equal to L3. So let's say that I were a particularly dense person, and I were studying a system with rotational invariance. And I worked very hard, and I discovered that there were two conserved quantities: the angular momentum corresponding in rotations about the x and y axes, respectively. Then I would need not work further to discover that the angular momentum around the z-axis is conserved. Instead, I could just compute the Poisson bracket between these two, and I would automatically discover that this third component is conserved. So the space of conserved quantities for a particle moving in 3 dimensions with rotational symmetry is the vector space of angular momenta, which has this, which obeys this relation that the commutator of Li with Lj is equal to Lk times the epsilon symbol. And so that algebra has a name. It's referred to as the SU2 or SO3 algebra. Or sometimes just referred to as the rotation algebra. It's the rotation algebra in 3 dimensions. You know, there are other names for the rotation algebra in higher dimensions. And so when you were studying your quantum mechanics class, you probably studied particles with spin and Pauli matrices and all that stuff. You guys did that, I assume. And you probably wondered why the hell it was that your generators of angular momenta, such as the Pauli matrices, have to obey this algebra. And this is the answer. The Pauli matrices are, in the mathematical language, what's called a representation of this algebra. They're a set of matrices which obey the same commutator relations as the generators of the angular momentum of a particle with rotational symmetry. So this explains why, when you were studying the quantum mechanics of a particle with spin, you started by looking for matrices acting on some vector space which obeyed this algebra of symmetries. So are there any questions on that? So let me give you a second, somewhat more sophisticated example. So let's consider the Kepler problem. Where we have a 1 over r squared attractive force, or 1 over r potential. Now, this Kepler problem is, if you go to center of mass coordinates, rotationally invariant. So we have the conserved angular momenta that I described above. But it turns out you also have an additional set of 3 conserved quantities, which are given by the following quantities. So 1 over m times p cross L, where L is r cross p, minus r hat, where r hat is the unit vector pointing in the radial direction. And one can check that indeed this turns out to be conserved. You can check by calculating its time derivative and inserting the equations of motion that A is independent of time. And I believe you did this on a problem set earlier in the semester. Is that correct? Yes. So now we're in a position to understand a bit better what these symmetries are and what they look like. So in particular, we have these three symmetries AI, where I runs from 1 up to 3. And you can check that the Poisson bracket of AI with LJ is again given by the epsilon symbol ijk times ak. So the Poisson bracket of L with A is equal to N. And the Poisson bracket of AI with AJ is also an epsilon symbol with L. So the commutator of L with L is L. The commutator of A with L is A. And the commutator of A with A is L. And so that means that the A's and the L's together form a larger algebra. This would now be a 6-dimensional algebra because I have 3 L's and 3 A's for a total of 6 conserved quantities. And there's a name for the algebra there's a name for the algebra with these 6 generators. It's called the SO4 algebra. And just as SO3 is the rotation algebra, the algebra of rotations in 3-dimensional space, SO4 is the algebra of rotations in 4-dimensional space. So secretly, even though you would think that the Kepler problem only is invariant under rotations in 3 dimensions because it's a particle moving in 3 freaking dimensions, right? Secretly, the Kepler problem is actually invariant under rotations in a 4-dimensional space rather than a 3-dimensional space. Now, this extra 4th dimension is not some oogie-boogie X-Files extra dimension or anything like that. It's just some additional auxiliary quantity which is constructed out of the positions and the momenta. But I think it's sort of remarkable that the fact that the Kepler problem, which is a particle moving in 3 dimensions, actually has the symmetries of a rotation in 4 dimensions. So there's one other place where you may have seen this algebra here, where the commutator of L with L is L, L with A is L, and A with A is L, with all of these epsilon symbols here. And that's in your class on special relativity. So in your class on special relativity, you learned that time and space should be treated on equal footing. And so you should really think of a 4-dimensional space-time rather than just space. And so that means that the algebra of transformations that leave special relativity invariant, the algebra of symmetries in special relativity, also looks sort of like a 4-dimensional set of rotation symmetries. And in special relativity, you had 3 rotations, and you had 3 additional symmetries, which are the boosts. And if you remember, the commutator of a rotation with a rotation is a rotation. The commutator of a rotation with a boost is a boost. And the commutator of a boost with a boost is a rotation. Did you guys see this in your special relativity class? You probably didn't. That would be an excellent problem for me to assign on a problem set then. But unfortunately, I've already written your problem set, printed it out. I don't want to waste paper. Should I waste paper and give you that problem on your problem set? It does sound like fun. Maybe I'll give it on your final instead. That's something to think about. Okay. Yeah. Yes, you have a question?
In quantum mechanics, we were studying 1 over R potential.
Yes.
And when the prof was talking about the degeneracy of energies, we said that And pi comes from the symmetry which gives angular momentum conservation, not only a symmetry in 4 dimensions. And this has
Yeah, there's so that's a great example. Was it 1 over r or 1 over r squared potential?
1 over r.
It was the fact that the orbit comes back on itself instead of persisting.
Oh, I see what you're saying. Yes. No, that's precisely this. That's precisely this fact that he was discussing. I thought, okay, so for a 1 over r potential, that's the Kepler problem, right? The hydrogen atom problem is the Kepler problem, except you call things charge instead of mass, right? And it's attractive because a proton and electron have opposite charge, right? Because okay. Just like in the Kepler problem. So the Kepler problem is the hydrogen atom. And that extra symmetry he was talking about is this SO4 symmetry. Now, I thought you were referring to a different example. If you have a 1 over r squared potential, there's another conserved quantity. I don't remember if I put this on your problem set or not. And that has to do with the scaling symmetry, or what's called a dilatation symmetry. That's another fun thing to work out. I know at one point I put it on a problem set. Maybe I decided to take it off this year. Maybe. We'll see. It'll be an adventure when you do your problem sets to see whether I assigned it. So yes, these symmetries are all over the place, and they're incredibly useful when you want to understand solutions to these equations. And yes, the extra dimension that your professor was talking about is precisely this SO4 symmetry. I mean, it's not a physical extra dimension. It's just some sort of mathematical artifact of the way that one can construct this system. So there's one. So are there any other questions before I continue? So there's one important question, however, that we have not yet answered. So remember in our discussion of Noether's theorem, the way that our discussion went is you first identify a symmetry of the system, and then from that symmetry you construct a conserved quantity. And the thing that we never understood in our discussion of Noether's theorem was, if I have a constant of motion, can I figure out what the corresponding symmetry is? Now, in some cases, that's very easy. If you have a linear momentum or an angular momentum, you know it's a translation or a rotation. But let's look at this case here. Let's look at this auxiliary SO4 symmetry of the Kepler problem. This A here is some very complicated function of the position and momentum. And it's a constant of motion. You can check, and you did check on your problem set, that it is independent of time. But it's not at all obvious from what we have done here how one can figure out what the symmetry associated with this is. Morally speaking, it should have something to do with the rotations in some oogie-boogie extra dimension. But how do we make that precise? How can one work out what the symmetry of the Kepler problem is that led to this conserved quantity? Now, I should actually mention, in the textbook, when they ask you to figure out that this thing is conserved, they actually ask you to try and guess what the corresponding symmetry is. And I hope when I assigned you to do that problem, I was careful to tell you not to try and do that part of the problem, because it's completely impossible. Or rather, it will be completely impossible until my next lecture, when we will learn, when we will sort of understand the full power of Noether's theorem, and we will understand how to generate a symmetry given a constant of motion. And so that's where we're going next. We're going to study the symmetries of the phase space formulation of Hamiltonian mechanics. So are there any questions before I continue? We only have 5 minutes left, so I won't try and give you a full description of that here. But maybe what I'll do is, well, I could either pause and see if there are any questions, or I could just whet your appetites a little bit. Any questions? Okay, yes.
You keep those
back to this relation between Poisson brackets and like the commutators in classical in quantum mechanics.
Yes.
But like, I don't really see how you would like. Is there a way to actually go from one to the other, or it just sort of seems like a coincidence that they have the same sort of algebra. Where you get the IH bars and stuff.
Good. Well, let's put it this way. Why was quantum mechanics developed in a formalism where positions and momenta don't commute and where observables are realized as operators acting on some Hilbert space? That's just the way that nature works is part of the answer. But the other part of the answer is that quantum mechanics was constructed from classical mechanics. And this is the formalism of classical mechanics in terms of which quantum mechanics was constructed. But now you could ask what I think is probably the more important question, which is the following. So if I give you a classical system, what is that classical system? You have a bunch of positions and momenta, and you have a Hamiltonian. And what you would like to try and do is quantize that system somehow. And the way that you want to try and quantize it is you want to replace your Poisson brackets with Dirac brackets, with commutators. You want to put IH bars in everywhere. And loosely speaking, you could just make the statement, oh, I'll put IH bars in everywhere. A Q and a P will give me, the Poisson bracket of Q and P being 1 will be replaced by Q and P being IH bar. And then I'll just work from there. But in fact, it turns out that that statement is not well defined. And I think this is one of the great mysteries of physics, really, which is how do you go from a classical system to a quantum system? And the basic answer is we don't know. As I told you, what data do you have when you construct a classical mechanical system? You have a phase space and you have a symplectic structure, which is essentially the structure of the Poisson bracket. And the question then is there a unique way of replacing that Poisson bracket by Dirac brackets? And the answer is sometimes. So for certain systems, there is a unique way of doing it, but for other systems, there is not. And so it turns out that there's there's only certain classical systems which have a unique quantization. And there are other classical systems which do not have a unique quantization. And this fact leads to all sorts of interesting physical effects. I think it's one of the very deep and mysterious facts about quantum physics that is not completely resolved. And that's partly why it's not discussed in your quantum mechanics classes. Your quantum mechanics professors probably presented quantum mechanics in the following way. You write down a classical Hamiltonian as a function of x's and p's. Then you replace your p's by dx's. And you imagine this Hamiltonian as an operator which acts on a Hilbert space of functions, which are your wave functions. And for certain Hamiltonians, that works fine. But for other Hamiltonians, that does not work. And there's no unique way of defining a quantum evolution, a Hilbert space, a Hamiltonian, and all that stuff. So, so there's a sense in which you have been lied to because you've been taught that quantum mechanics is completely well understood, but that's not the case. So what I'm referring to is called the problem of quantization. In many cases, if your phase space has a certain structure, then the problem of quantization can be solved, but it's simply not understood in general. Sorry, that was a very long-winded way of answering your question. Are there any other questions? I mean, it's a very deep question. How do you replace the algebra of functions on phase space by an algebra of observables in quantum mechanics? In classical mechanics, you don't have a Hilbert space. So what is the right Hilbert space for you to construct in quantum mechanics? You've just been flying by the seat of your pants so far in your quantum mechanics class. You just sort of guess what the Hilbert space is. And so far, you've always guessed the right answer because you have professors who are telling you what the right answer is. But it's not, for an arbitrary classical system, it's just not completely well defined how to quantize it. That is I mean, that, and it's that basic fact which leads to a lot of the problems that people spend a lot of time thinking about in physics today. So, yeah. Any other questions? Okay, I don't have time to whet your appetites, I guess. Any other questions before we take off? All right, I'll see you guys on Tuesday.